SwayamPrabha. Digital India. Educated India.
Hello everyone, this is the third lecture of this week. In the last class we started discussion on finite element methods in three-dimensional problem, and we will continue that discussion today. As I said in the last class, our discussion on three-dimensional problem will not be very detailed and in-depth. Rather, we will just browse through the basics of finite element methods applied to three-dimensional problem. Whatever we have learned so far in 1D and 2-dimensional problem, the same concept we will extend for three-dimensional problems. Okay. Now, in the last class, we had seen some of the commonly used elements in 3 dimension, and we had seen how to construct a function for some of them. And today, we will see what is the isoparametric formulation and numerical integration in 3-dimensional problem. So, we already know what is isoparametric formulation. Now, if we again see the same or discuss the same, the premise will remain same, but now the isoparametric formulation is applied to 3-dimensional problem. Okay, so we have a problem, discrete domain, discretized with some 3-dimensional element, and then we take one element, and then this is the element, right? Now we need to write the equations for this element, but because of the shape of the element, orientation of the element, we cannot write the equation directly for this element in xy coordinate system. So this is xy coordinate system, the element is. Then we take an element in its parametric space in xi, eta and zeta coordinate, which is also called the natural coordinate, and the parametric space is -1 to 1 in all the directions, zeta, eta and xi, eta and zeta direction. So this is our parametric domain, and this is the parametric domain, and this is our physical domain, right? Now, so once we have this physical domain and parametric domain, we need to define a map between this parametric and physical domain, and this map is the definition of this map. We will see, we have already seen in isoparametric formulation what is that map. We had also seen for subparametric and superparametric case also what is this map. Now in isoparametric formulation, the idea is the shape function that we used for the field variables, the same shape function is used for the geometry as well, right? Now, this is isoparametric formulation, right? Now, let's see what is that map in case of 3-dimensional problem. So, any field variable u is described with respect to the shape function, phi I are the shape function, n is the number of nodes we have in the system, in the element. We have seen for brick element and tetrahedral element what are these shape functions. Okay. Now, this is how the field variable is approximated over this element, and then the geometry, mapping of the geometry between the parametric space and the physical domain is also through the same shape function. Okay. So, x, y, z are also written in terms of the shape function, whether the x, c, y and z, e are the, or xi, yi and the zdi are the coordinates of the nodal coordinates in its physical domain. Xi, eta, zeta are the natural coordinates, and then x, y, z is the corresponding, if we have any point here, any point in the parametric space, and this point is mapped to this physical domain through this transformation. Okay. Now, once we have this geometric map, then the next is to define the Jacobian. Jacobian essentially gives you how the derivatives are related with respect to the physical domain and the derivative with respect to the natural coordinate system, parametric domain. So this is how the Jacobian is written. We had seen the expression of such Jacobian. Now, once we have this Jacobian, then the expression, this derivative of this x, y, z can be written from this expression. And for this element, it is the summation will be over the over node number 1 to 8, but if it is a tetrahedral element, then the summation will be over 1 to 4, and it all depends on the how many nodes we have in the element. So we know this. It is just the same Jacobian written in 3-dimensional case. Okay. Now, once we have this Jacobian, see, when we write, then eventually we have to write the element equation, and then after once the element equation is written, then globalization, then solution, whether it is 2D problem or 3D problem, those things are almost similar. Now, when we writing element level equations require this mapping, these are isoparametric formulation, right? Now, once and another thing is required is the integration. Now, this, if you recall, this integration we have done in case of quadrilateral element or triangular element through Gaussian quadrature technique, and this is how the Gaussian, this is what the Gaussian quadrature technique is. We have to write an integration over a domain, any 2-dimensional domain, and then this is mapped with a parametric domain, and the Jacobian is that map. Jacobian is the actually carries the information about that map, and then idea is we take some integration points which are known as which are also known as Gauss points, and then evaluate the function at that Gauss point, and then multiply by the weight and take the summation to get this integration, and where Wi, Wj are the weights associated with the integration point, and xi and eta j are the integration points, and ngp is the rule of the integration, means how many integration points you have in each direction. So this is where ngp is equal to 1, means we have just 1 point, ngp is equal to 2, means in xi direction we have 2 points, eta direction we have 2 points, so total number of points is 4. It is ngp is 3, in xi direction is 3, eta direction is 3, and total number of integration points are point is 9. So the same concept now we can extend to a brick element, tetrahedral element. For instance, this integration now needs to be defined, and the f is now the function of x, y, z both, and d omega is this omega e is a 3-dimensional domain. Now, this integration can be written in terms of xi eta coordinate system as now xi eta and zeta coordinate system as this, right? And then the idea is this integration is now can be written as a summation, and this summation will be over xi direction and then eta direction and then zeta direction. We will take some integration points within the domain and then multiply by their, evaluate the integrand at those points, multiply by the weights and get the integration. So for instance, suppose this is our parametric domain. This is the domain -1 to 1 in each direction, and now takes this is in xi, eta and zeta direction coordinate system. Take some integration points, and then these are the integration points. The red points you can see, these are the integration points. So in this case it is ngp is 2, because in all the directions, xi, eta and zeta direction, the number of points is 2. So total number of points in this case is 8. So evaluate this value at all 8 points, multiply by their weights and sum them to get the integration. The same concept we can it is the same concept that we have already used for quadrilateral element. Now these are the positions of these locations of these integration points, and these are the corresponding weights. And you will see this is also similar what we have already done for quadrilateral element. So this is for the integration over hexahedral domain or brick domain. Now we also know how to write this integration over a triangular domain. This is how the integration is performed, and it is again same. And xi1, these are some Gauss points, integration points, and then the same concept can be extended to for tetrahedral domain. tetrahedral element. This is the integration. This is the tetrahedral element. Now xi1, xi2, xi3 and xi4 are the triangular coordinates, are the area coordinate system we had seen. Now, and xi1, xi2, xi3, xi4, their summation will be always 1, and the xi1 will be 1 at node number 1, and all other points it will be 0. Xi2 will be 1 at node number 2, all other points it will be 0. So now xi1, xi2, xi3 are the position of those integration points in the respective coordinate in the direction, and these are the corresponding weights. So this is how the integration can be performed in tetrahedral element, right? Now, so once we know the integration, now let us take one example. For instance, take heat conduction example. Take the governing equation and then see what will be the finite element form of that governing equation, element level equation in case of 3-dimensional problem. So recall, it is in case of 2-dimensional problem, this was the Poisson's equation. This is the Poisson's equation, and which is the special case of a very general 2-dimensional equation we started, and this gives the special case with all these coefficients for these values. And finally, we have element level equation is this, and Fe will give you the source term, and QE will be the boundary flux term, and then B matrix is defined as this, and N will be the number of nodes, right? Now the same thing we can write for a 3-dimensional element as well. This is the governing equation. Now this equation is, now this operator is now in 3 dimension. We have del x term, del y term, and del z term, and this is the equation. And now the coefficient matrix will be like this: integration over dx, dy, dz, and then source term will be this, and then finally the boundary flux term will be this. In case of 2-dimensional problem, this boundary flux term, the boundary flux term was, this is just this s, it is just on a line, it is a line integral, but in 3-dimensional problem this will be a surface, okay? And this Kc will be a 3x3 matrix, and these Fe and Qe are the nodal values at different nodes, and Ey are the Ey is the degrees of freedom. In this case, it could be temperature at different node, and this is the B matrix, right? Now, similar thing if we have a brick element, the same thing for a brick element. Now, this matrix will be, in case of tetrahedral element, this was a 3x4 matrix, because we had 4 nodes in the element. In case of brick element, this will be 3x8 matrix, because there are total 8 nodes, and all these total 8 degrees of freedom we have, but rest of the things remain same. Now, so again I repeat, in order to calculate the boundary flux term, this boundary integral, if you recall, in case of 2-dimensional problem, the boundary integral needed to be performed on boundary which coincide with the natural boundary conditions, right? The case is same even in case of 3-dimensional problem. Only it has to be, this integration has to be performed. These are now our boundary of the elements are the surfaces, right? These are the boundary of the elements. So this integration needs to be performed on the boundary which coincide with the natural boundary. Suppose if you have some natural boundary defined on this boundary, say boundary 2, 3, 7, 6. So this integration has to be performed on this surface. So this integration will be a 2-dimension on the surface. Similarly, if you have natural boundary condition defined on this surface 1, 2, 6, 5, then this has to be integrated. This integration needs to be performed only on this boundary, okay? But on other boundaries, internal boundaries, these integration we do not have to perform this integration. This is same. Now, once we have this is, please note, all these equations that you can see on your screen, this is written with respect to the x, y, z coordinate system, right? This is x, y, z coordinate system. But now this needs to be written in terms of natural coordinate system, xi, eta coordinate system, xi, eta and zeta coordinate system, and then perform the integration. So how it is to be done? So through this mapping, we already know this map. Through this mapping, the derivatives are now really derivative with respect to x, y, z now related to derivative with respect to xi, eta, zeta through this relation. And when J is the Jacobian, we have seen what is the expression for the Jacobian. Now, B matrix is a function of x, y, z, and B matrix involves derivative with respect to x, y, z. Now, this derivative with respect to x, y, z needs to be replaced or needs to be represented by the derivative with respect to xi, eta and zeta coordinate through this relation. And if we take these two, and then this will give us the B matrix as a function of xi, eta and zeta. And zeta as this. So, now once the B matrix is written in terms of xi, eta and zeta and substitute this B matrix here, this entire thing is now written as a function of the natural coordinates, and then finally our coefficient matrix will be this. Once it is done, then same numerical integration technique we can apply to get the coefficient matrix, where wi, wj, wk are the weights and xi, these are the integration points, and beta and b already we have represented in terms of the natural coordinate. Now, once we have this coefficient matrix, similarly we can write the boundary flux term, and then we can write the source term, and then finally we have the element level equations. Now, once we have the element level equation, next is the globalization of the equation, assembling all these equations to get the global matrix. This procedure is exactly same. That assembling needs to be done based on the connectivity of the elements. And once we have the global matrix, then applying the boundary condition, get the partition matrix, and then corresponding condensed equations, solution of the condensed equations, everything will be exactly same. We have already discussed in case of two-dimensional and one-dimensional problem. Okay, so I leave it to you to extend the entire. We have not done any specific example here, but I leave it to you because we had a detailed discussion on the example of two-dimensional problem and also one-dimensional problem. Now, once we understand the essence of finite element in 3 dimension, now I leave it to you to apply this for a specific problem and get the solution. Okay, so let us stop here today. We will continue this discussion even in the next class. So let us stop here today. See you in the next class. Thank you.